for space mission. I welcome Prempal and about 15 minutes.
Thank you, sir, for your kind words. Good evening, everyone. We have got 15 minutes, but I will try to finish within 10 or 12 minutes itself, because I think you all are listening lectures from yesterday morning itself, and I know that you have got bored. That's why I will finish that. My topic is the challenges and opportunities in development of composites for space applications. Slide is not changing. It's not changing.
Oh, yeah.
Outline of the presentation goes like that: introduction, composites and its classification, composite in space-borne applications, basic design approach, manufacturing and scope of the research. These are the three major characterization of the space applications. Start with the space application, what is the required, then space infrastructure, what is to be built, and how it build the spacecraft, it should be launched and placed in the orbit, correct orbit. This slide I will skip, I think Nitin sir has covered this. This is the space infrastructure. For different applications, different type of the satellites you have to make, just like communication, earth observation, scientific research, small satellites for the student and research purpose. And these are the right side is the application of the satellite mentioned, that mobile communication, DTH, telecommunication, meteorology, disaster management, and etc. Space-borne components, generally we have to focus on three things. First is the high specific strength and stiffness is required for the material to be used or to be launched to be used in the spacecraft. Second is that it should be dimensionally stable, means it should be low CTE, low CME, and all. And third is the for application purpose, it should be laterally conductive. This is the composite material basic definition is there. I think everyone knows it. Then I will skip this slide. This is the classification of the composites. Major classification, I think everyone we are aware of. Composites offer, these are the main the properties of the composite which offers, and which we are glad to use we are glad to use or optimize these properties of the composites for our specific structures: lightweight, high specific strength and stiffness, customizability or multifunctional, means we can use as per our requirement, corrosion resistant, dimensional stability because of the low CT, adaptive over the complex shapes. It can take the, just like previous presentation, it was the mold. However, the good mold we are making, it can take the shape of the mold itself. And high impact strength because of the resin presence, creep and dimensional stability, wear resistance, electrical and thermal property. Research is going on to improve the electrical and thermal property, but somehow we are able to manage till now. These are the key application of the composites in the spacecraft. Basically, some of the large or the major components which is used in the spacecraft, it is mentioned here. The satellite payloads are the main component or the main heart of the satellite. It has to work as per the application or as per the user. The launch vehicle is the very big part of the, means it consumes almost 99% of the weight in any mission. But we have to see the specific requirement of the launch vehicle, and we are slowly converging the all components in the launch vehicle also in the composites to save the mass and to increase the payload capacity. Spacecraft is the highly required that it should be as minimum as possible, and as it is strength and the weight specific strength should be as high as possible. Thermal and altitude control, because it has to work in almost 10 to 15 years in the orbit, so it has to be thermally stable. Heat shield in early composite technology, we have used the heat shield to protect our payload from the heat while going in the space. Composites in spacecraft, basically we are using for three major properties. First is the dimensional stability due to low CT. Second is strength and stiffness. Mostly mechanical properties you are all aware, but we can focus more on the dimension stability because our spacecraft antennas are or other payloads elements which has to work for long year in the space. Strength and stiffness it has to be required only for the launch, but it is also necessary. These are the major space structures which is here you can see image is very low. That word are very written in the font size is very low, but I will read it. Measure the solar panel substrate. They made of the CFRP composites. See antennas, all big antennas. We cannot make it in the metal because it is very difficult to achieve the stiffness requirement in the metal and weight also. These are the satellite components. These are the realized hardware. As you left side, you can see that panels are realized with the CFRP honeycomb panels. Center cylinder is there, and the all four sides, four panels are there. And the right side image, topmost image, the reflector antenna is there, and the just below it is a filament binding process of the composites for the gas bottles we are using. These are the major challenges here. We can this is the main topic of that presentation. Major challenge for the material to be used in the space. First is the here all different categorized I have mentioned here. First is the environmental challenge because in the space environment is very harsh. Temperature goes like from -180 to +180. Radiation solar flakes are there, so radiation is very high. So our polymer matrix composite or polymers used to get degraded as per the time. Outgassing is the vacuum in vacuum and harsh temperature. Outgassing is also a big problem for us. And the micromaterial and debris impact. Second is the manufacturing and design challenge, which we have to take care at the ground itself. Large structure production is very difficult because of the most of the ultra high stiffness composites or ultra high stiffness prepregs fabrics we are getting in the prepreg forms. So we have to make the material also along with the product. Second is the defect controls. So we have to be very careful while processing to control the defects. Structural health monitoring. This is the new area of the research where we can monitor the structure of the composites during the service life. Weak transverse properties because along the fiber we are getting very high value of the strength and stiffness, but normal to fiber its value is very high. It's only polymer. Brittleness of the composites. It's a characteristic of the composite that it fails in the brittle until it is the brittle in nature. That's why we have to work. Means we have to load very low at the ultimate strength. Operational and cost challenges. Cost is a major role for the composites that it has to be survive in the market, or it has to be. We have to study that how much mass we are saving how much fuel we are saving to use that composite to save the cost. It requires high production cost. Initial investment is very high. Complex manufacturing, material degradation in the lifetimes. Repair and recycling cost. Repair, recycle, and disposable. Also, it's a challenge for the composites because first we have to investigate that which kind of defects is there. Then we have to think about how we can repair it, and after repairing, we have to ensure that it has been repaired. Other consideration are that techniques. Composite earlier speaker also said that composite is a process oriented material. Means it is highly dependent on the process. And the damage accessibility, we have to do the real time damage accessibility. And compatibility is also, we have to, in the hybrid manufacturing, we have to see it is compatible with other components or not. These are the advanced composite in space structures. This is the general classification only. We can skip that. Current research and future trends. Here we can see that we have to increase somewhere we have to thermally isolate one component from the others, where composite is acting as a very good thermal isolation. But sometimes we require the thermally conductive to conduct the heat from one place to other place. Or electrical property also conductive to act as a reflector or antenna. So we have to increase the thermal and electrical conductivity of the composite structures. And the radiation resistance, because due to the radiation, polymer property gets degraded. So we have to make the composite such that it should be at least in working life, it should be stable. Self-healing composites we can work on that. Some small cracks are there, then it can heal itself by itself, just like our skin. in situ polymerization, there in nowadays for the high to go, if you are using that, if your working temperature is more than 100 or 150, we have to use the thermostats only. So thermostats require at least minimum 1.5 hour polymerization time. So we can do at least in the repair work, if in situ polymerization is working, then we can repair our damages easily. And thermoplastics working temperature also we can increase. Advanced radiation shielding, additive manufacturing also is there. Novel materials, we can find out the new materials which can be inspired by bio inspired or nano composites, hybrid composites, multifunctional, multi-scale composites. Manufacturing process also we can improve by 3D printing itself. Modeling or characterization we can improve. Now all only technical presentation is there. We can skip all this and go on. Here we can see that scope of the research in the current composite technology is that to increase, we have to increase now rigid. Our payload ferrying capacity is only 3 meter, 3.5 meter, so we can make antenna up to 3 meters. So if you are able to make, if you make the composite structure like flexible resonance system or high strain resonance system, we can make the antenna, we can increase the antenna size up to 5 to 6 meters. So we can stop during the launch and open after launch. 3D woven carbon fabric, we can give carbon only in the required specific directions by this technology. Development of the CFRP component and the metallization, so we can use the RF elements also. Optimization of the CND process to increase the electrical conductivity. Improve the electrical and thermal conductivity of the CFRP component. 3D printing of the CFRP, so we can give the complex shapes also, irrespective of the mold. These are the some that images.